Hello, and good evening from the woods of Maine. Where it is currently ice, rain, snow. Pretty much most people would consider it abysmal, but I always like the weather when it's at its absolute worst, so I don't mind it. But anyway, it's a great day to record, and away we go. Um, when I left off, I believe I had gone through the basically the guts of New England and the formation of it, um, as depicted over here by this very large oval right here. We went through the tectonic orogeny, which is essentially this area right here. And then over time, this was the tectonic up here that built this range right here. We had the closing of the tectonic seaway, and then behind it, as the tectonic seaway closed, we had a couple of island arcs associated with that closure, and one is here and one is here. And then behind it is a chunk of oceanic crust of the Iapetus Ocean, as well as some chunks of northern Amazonia, which today is presently the north part of South America. And then in between that is an ocean, which is going to, or a seaway, which is also going to close. Oftentimes between these island arcs, an ocean or a seaway will be there, and they will end up being smashed as the conveyor belt of land gets compressed into Laurentia. And Central Maine Trough is an island. Is basically the majority of the Iapetus Ocean sediments. Then you have another trough right here associated with the approaching, probably the trench of Avalonia as it approached, and then Avalonia hit, which is right here. This is a chunk of northern Africa. And then another exotic terrain called Meguma, which we don't really talk about because that really doesn't have a lot to do with us. So stage 2, Gandaria, which is this area right here, that would be considered Gandaria, with a subducting trench. The subduction is going underneath this area right here, as well as Laurentia, Gandaria welds, and then another subduction zone forms behind Gandaria, which creates a trough right here. This is the Merrimack Trough as Avalonia approaches, which is this area right here. And then eventually Avalonia crashes in to North America, or Laurentia rather, and all of these zones that you see here are now all compressed and pancaked against Laurentia. And this depiction shows it perfectly. You have the Gandaria exotic terrain, you have slab breakoff, you have the Avalonia approaching and now contacting, and then you have the slab of the Araic Ocean going under here. And then, of course, Meguma follows behind that, in which case there would be some sort of a subduction zone coming here or here, depending, represented here. And then finally you have Meguma, Avalonia, Gandaria, and then all of the associated island arcs and exotic terrains of Gandaria, all smashed into the trough right here, which is against Laurentia, which is right here. And eventually, Gondwana, which is essentially Africa, or the majority of the southern continent, is going to combine and close everything. And that's going to take another probably about 70, 80 million years. All right, so as these terrains approach, they generally there'll be some sort of a trench before them, and these trenches fill up with debris or detrital sediments, either from here or from here. Because as this approached, there was a waterway right in front of us between here and here, and as this slice of continental crust eroded, it was depositing material into these troughs, and that's what I'm about to show you. And it is these troughs right in here and here that make up the majority of what we see on the marginal wave. And they are sediments derived mostly from the Avalon terrain, we think, and some of it from the Gandaria island arcs as well, as they approached. And this unit, the sedimentary unit, rock unit, is known as the Kittery Formation. It is pretty famous It is very well known, very well studied. And just imagine sort of an area between here in Portland, well, maybe Scarborough, maybe Saco, down to Portsmouth into New Hampshire, maybe approaching the sort of near Epping or Exeter area, and then sort of coming up through the Berwicks, and then sort of following parallel to the coastline and sort of enclosing uh, the rectangle sort of up near Scarborough. And that area was once a trench or a trough or an ocean bottom of the approaching Avalonia microcontinent. And we think that the majority of the sediments that you see on the marginal way were actually deposited from the approaching landmass from the east. So the sediments that make up the marginal way did not come from what you would think right now, because most of the land is all to the west of us, that it would have come from there. It did not. It came from an approaching island arc or microcontinent, Avalonia. And we know this because we take certain grains out of this. You can take zircons if you can find them in here. There are some other minerals that you can do this with, but in any case, if you can date these, not date these, but if you can get geochemistry of the actual grains of sands, you can tell whether or not they are derived from North America or from the Avalonia microcontinent. And the geochemistry indicates that the majority of these grains in here are along the marginal way in the Kittery Formation are in fact derived from the east. We see that also in the bedding. But this is the source of the sand and the muds and the clays. So what was happening as this area was approaching, it eroded, it dropped stuff off into the sea between Laurentia and Avalonia, and there was a shelf and a continental slope, and eventually these things would pile up, the sands or the muds or the silts, and they would avalanche down as turbidity currents and make layers and spread out in a westward direction. And that made the Kittery Formation, which we see all over the margin way. It's light and dark, alternating light and dark layers, darks being phyllite, which is a silt layer, mud or silt that has been metamorphosed into a very sort of a medium grade metamorphic rock. And then the light colors are sands, which are now quartzites, because sand is mostly made up of quartz. So as you can see here, I put a gunkwit kind of somewhere in the middle of this. I mean, who really knows? But we know that it's getting sediment from this source coming this way. Approaching Avalon microcontinent from the east, sediments derived from both east and west throughout New England, but you would have to go out, basically out towards the New Hampshire border to start to see sediments from the west. Mount Washington here, in fact, does show that sediments were derived from the east. So even near Mount Washington, we do see turbidity currents coming from the east and not the west. Ogunquit is located further east, so therefore it must have also received sediments from Avalonia microcontinent. The Kittery Formation is a mixture of sand, silt, seen as alternating light and dark layers, deposited as turbidity sediments offshore of the Avalonia microcontinent. Yes, we went through that. And this is just a more simplified diagram of it. You got Avalonia here, you got a continental shelf, stuff piles up, and then it extends out and eventually collapses and then avalanches. And depending on your area, you're going to get different layers. So if it avalanches low, you're going to get silts and fines. If it's in the medium, you're going to get medium is silts and fines. Very, very low out there is very clays, very fines. And if it's up high, you get the sand. But in either case, this is one, and then a second one, and a third one, and then it just keeps repeating, and it keeps making these layers. And if you cut this down the middle as they pile up, it looks like just layers of almost like shingles stacked on top of each other. But some are light and some are dark. So the Kittery Formation. Dun, dun, dun. This is all over Ogunquit, all over the southern, southwestern coastline of Maine. It feels weird to say that because it's on the, it's the east, but so the whole area between, let's just say Scarborough down somewhere to like Epping, you're going to find the Kittery Formation. It's a fairly, so that's probably what, 20, maybe 60 miles, 100 miles long, and maybe, I don't know, 30, 40, 50 miles wide. I don't know. It's probably bigger than that at one time, but that's what we see of it really now. So the general lithologic descriptions: Kittery Formation is an early Silurian green schist to amphibole facies, supposed to be facies, turbidite sequence with variable lime, sandy, and sulfidic phyllite beds. That's from Dr. Hussey, his classification of it. Um, so the primary sedimentary structures preserved for this unit are graded bedding, flute cast, flute structures, occasional rip-up mud, glass, small-scale cross-laminations, and channel cut and fill structures. That's just basically your common ocean bottom that has in a fairly I don't think it was super deep, but these are just generally structures that you see that are found by bioerosion, turbidity currents, maybe even storms. But these are all part of the continental slope sequence. And stratigraphy, Reicherich used the primary sedimentary structures as the westward direction of these structures to interpret the Critteri Formation as lobes of fans of a submarine fan in a continental rise environment. So westward directions means that it was coming from the east and traveling west. He also proposed that the primary sedimentary structures suggested an eastward depositional source in present day with, if you look at it in today's coordinates, interbedded with contrarite deposits from the northwest flowing current. So there you go, Kittery Formation. And here's what it looks like. This is right near, it's known sometimes as Devil's Kitchen. We always knew it as Pounder's Cavern. It's on the marginal way. It's the largest crevice of the path, and it's just west of the, not west, it is just east of the lighthouse, or towards the cove, Perkins Cove. And each one of these is essentially sands being deposited and laid down in turbidity currents. And depending on the actual thickness of it, you're going to see some are thicker and some are thinner. So these are thinner and these are more thicker. But here's the alternating light and dark layers being phyllite, light layers being sandstone, mixed. Some that are stained are basically a mixture of both. You see them down here as well. And with this, we pretty much are thinking that when you see something like this, on this picture here, it's kind of confusing. We think direction was this way, as as indicated down here. Although Hussey always claimed that these are turned upside down. So if that's the case, yeah, current would have been going that way. It also would have been going this way. Okay, so yeah, if these were turned upside down, the current would have been coming that way. So anyway, this is sort of what you see out in the field, and you get current direction going this way, and it lobes over each time, and then you get another one that lobes over each time, and that's just the way that these things form. Kittery Formation in York, Maine. This is the cliff house. So these beds are actually almost vertical, so we don't really have a. I guess you can tell which way which way up was by looking at the individual layers and figuring out, well, the rough stuff's going to be on the bottom, and then it grades up into fine stuff. That's kind of what we look for. This right here, look at that. It's a nice, looks like a sort of a felsic dike cross-cutting the formation. But these are almost literally 90 degrees. This right here, it's different than, even though it's 90 degrees straight, this is a sill, I guess it would have been at the time. It's now, it looks like a dike, but because it's turned upright. But it actually went parallel to the bedding layers, and basically this is a diorite cliff, I believe, and it's made of igneous rock. It's very hard, and that's why it stands in relief to the adjacent layers. So, anyways, each one of these formations are incredible. It's just, I forget which way top is. I'd have to go out there and look. And even when I'm out there and I look and I try to figure it out, sometimes I think I nail it, and then I look at something else and it confuses me. And what we look for is when you have a turbidity current, basically the big stuff's going to move very quickly through. And then you're going to have basically larger grains first, and then finer grains after, and then you find, and then there's abrupt change, and then you have larger grains, and then it grades into finer grains, and that's how you can tell. So it's either this way or this way. You'd have to go out and look. I don't remember off the top of my head. This is a geologic map of southern Maine. Got Kittery here, Cape Nettic, Gunquit here, Marginal Way right there. And this is the Kittery Formation right here. Kind of just goes down here through Portsmouth, up here through Biddeford, continues on, actually, probably up to Scarborough. This one behind it's similar, but this is pretty much the extent of the Kittery Formation. And within this Kittery Formation, we have these blobs that pop up, and these are actually these are igneous centers. This is the Egomenikus complex. It erupted in the Triassic. Interesting note of this is that it produces both a granite and a syenite. So it had a couple of different things going on with it. And syenite is just basically a green granite where you have chlorite kind of replacing the quartz. And interesting of this particular eruptive center, did it produce volcanoes? Most likely. It's big enough where it could have done that. Just depends how much crust it had to punch through to do it. And in the Triassic, we can assume that we've had some erosion go on, so it may well have produced volcanoes. We also have another intrusion right here, but this is mostly a felsic intrusion, and we believe it's related to the Mount Washington and igneous complex, meaning that in the late, I'm not sure if there is in the Permian, but I know in the Triassic, we have in the Jurassic and what have you in the Cretaceous, we have volcanic volcanic epicenters like this, or volcanic intrusions like this that make up Ossipee complex. There's some near Mount Washington. There's a Conway complex, and then if you go on the other side of Mount Washington, there's other igneous intrusions that, and chemically, these all seem to fit the bill. They all seem very related. And then these intrusions continue off all the way out to the mid-ocean ridge, and then they're even on the other side of the ridge where the hot spot is. So this is related to a hot spot, possibly the continent moving over a hot spot that's been around since probably the Permian time. This is another one right here. That's another igneous intrusion. And then these here, these are granites. These are much different. They are in the Devonian time, so they are a good 200 million years older than this right here. And we know that because this cross-cuts this, and not just that, but we also dated them. These are related to subduction, possibly subduction of Avalonia on its way to North America. So there was a subduction zone in this area, a subducting slab. It may have melted and produced these basaltic, these granites. Granites are very common in island arcs, especially down in the guts of them. And they will form over areas where subducting slabs are going. So we think that these are related to subduction that came from the east and was subducting west. And that was during the Devonian time, because right after that, this is when Avalonia came, and then soon after that, in the Carboniferous, we had Africa. But so since these are Devonian age, it would be likely that would be the source of that, or related to some sort of island arc. But I doubt it, because you have sediments here that have been already laid down, and these are significantly older. So I believe that these are related to subduction. That's my story. Sticking to it. So this is the Acadian Orogeny deformation. The Acadian Orogeny essentially affected it is the orogeny of New England, and this is the outline of it. So, Maine border right here, basically you know, this is the top of New Hampshire, Vermont. So this is the Vermont. These are the Green Mountains. They aren't part of the Acadian, but they definitely got heated from it. But everything else from, we'll just say the New Hampshire line forward, all the way through to Nova Scotia, PEI, and even up through Newfoundland and Labrador, that is all Acadian orogeny deformation. And these are the various units. The pinks, right here, this is the, these are ocean sediments. These are arcs up in here. And the more ocean sediments right here. You've got intrusions. And then you have, this is a slice of Avalonia right here. More ocean sediments right here. And then you have Avalonia back over here. This is just basically the Iapetus Ocean all the way right up through here. And this is just a generalized map. You have the Avalonia terrain here and here, and then everything else. So you have continental crust. You have the giant Norimbuga Fault, which is essentially very much like the strike slip fault of today's San Andreas. And then everything else in here is volcanic islands and ocean floor sediments, as I said earlier. Tectonic map, just again hammering that point. Anything in yellow is ocean related. Basically, these are ocean sediments, island arcs, volcanic arcs, whatever. Anything over here in this red is Avalonia. Everything in the back here is either Laurentia. Actually, this part right here is the Laurentia foreland. And then this green right here, this is all these are all Mesoproterozoic Grenville rocks. Very much older than anything else. And here are the terrains. These are the terrains. You have the Grenville terrain here that was formed and built between 1.25 and 0.9 billion years ago. You have the volcanic island arc of the Taconic orogeny between 480 to 440 million years ago. You have a trough right in between here. You have a volcanic island arc here around 400 million years ago. You have a volcanic arc here, probably about 420 maybe. You have the Iapetus Ocean. This is actually the Rheic Ocean, but it's a part of the Iapetus, so it works. You also have a seaway here. This would be really the Iapetus right here, and then this is the Rheic right here, separated by these arcs. And this is just probably another seaway. So you have synclines, anticline, syncline, anticline, syncline, anticline. And any places the anticline is a mountain range or an island arc. So island arc, ocean sediments, island arc, ocean sediments, island arc, ocean sediments, island arc, continent. And that's how it worked. So if you were going to look at the, if you were going to get an idea of what New England looked like 360 million years ago as Avalonia was on its way, and probably, you know, it had its crosshairs set on New England, and we could see it. Well, I don't know if you could see it at the time, but anyways, as it started to deform the Gandaria terrain, or even the Taconic terrain, you would see something that probably looked like this. This is the foreland of the Himalayas. It is on its way up. It is just beginning to build. These mountains are probably in the order of, I don't know, since it's on the equator. Actually, this is not, yeah, Himalaya foreland. Okay, yeah, so about 10 to 16,000 feet. So that makes sense. These, the only difference is you just wouldn't see the trees like this. It would look a little bit different, but this is kind of what you'd see. You'd see mountains that are literally being arched up. You see all these faults right here too, as it's being lifted. So this is what New England probably looked like around that time. These are the Devonian period landscapes. These are what we would call trees of the Devonian. I apologize, I do not know the names of these, and I should. And every time I do this, I'm like, oh, I should check that. But I do not know. And I do not know what these are. What I do know is that these are amphibian-like reptiles that are, yeah, they're amphibian-type reptiles. They are now, the amphibians are making their way to land, and they are beginning to invade the land. But yet these are probably still needing to go back to the water, because you really don't get the true land stuff. I think in the Carboniferous, the lands, you get that's when land animals really start taking over. But you got sparse vegetation, a lot of swamp, and then you have the amphibians that are truly beginning to evolve into true reptiles. And this is what you would see. This is a tectonic map of the Mississippian period, 345 million years ago. And what this is showing us, so the Acadian orogeny has occurred. We are here, we are smack dab in all of this stuff right here, slammed into North America, or Laurentia rather, and built a mountain range right here in the order of between, we'll just say 14 to 16,000 feet. Maybe a little higher, maybe even getting close to 20, but we have a very large mountain range in New England, and we have a trench offshore. This is Avalonia. Maguma might be here, might be out here. I don't know. It's hard to tell. Maybe this is Maguma, but anyways, this is New England. It has had a series of island arcs, and the Avalonia subcontinent or microcontinent slam into it, and now the Iapetus Ocean is finally closing, and here is Africa, here is South America, and they are about to make contact very soon here. Carboniferous period. This is the Mississippian. It's part of the Carboniferous, just depending on which country you're talking or you learn geology from. And this is 325 million years ago. We now have contact. Africa is now starting to deform the mid-Atlantic coast, and it's beginning to close the zipper both southwest and northeast. And here we are, the Mississippian period. The tectonics are right here. So we had Avalonia, boom, slammed into it. This is the Acadian orogeny. Africa is now en route, and we are closing what remains left of the Iapetus Ocean. And we are right between here and here, so I put us right about here. I would just bring this to about the point right here, and that would be about where we are on this line right here. And our depositional environment consists of, we got carbonate deposition here because this is on the equator, probably warm and nice. You probably have, you have a very high mountain range right here. Lot of volcanic activity. Prevailing winds would have been blowing, this might be ash out in here. Maybe that's one of the reasons you have a basin here. You have non-marine sediment, so this is the land right here. You have the Franklin Highlands up here, and Africa is now approaching, and there's a trough somewhere in here that's going to be filling up. And this is what we would see New England at about 350 million years ago. You would see mountains that looked kind of like you would have a very high mountain range, and it would be literally something probably just like the Alps. I think that's a great analogy. It's about the same size. Got the Matterhorn right here. There's so much geology going on in here, I don't even want to try to describe it, but the gist of it is that the funny thing is that the top of the mountain, the Matterhorn, is actually older than the basement of it. So in other words, this piece here got thrust up over this piece down here, and when you do thrust faults, you can always tell the thrust fault because it's defined by the fact that an older piece got moved up over a younger piece, and that defines generally a thrust fault. And New England about 330 million years ago, we're getting close to the actual continent-continent collision. And as Africa is approaching, you've got a trench and everything like that. You'd have mountains that probably look something like this in New England. And maybe close to this because there's not any plants really here. So yeah, this would be about right. So you're looking at mountains that are now approaching about 20,000 feet. There's a lot going on, and they are eroding, and it make these, especially since we're located near the equator or getting close to it, which means we have massive amounts of erosion occurring. And this plays an important role in the Carboniferous. With this mountain range located near the equator, we have a lot of, let's go back one. We go back here, when you have a large mountain range and a landmass that near the equator, it erodes very quickly because, let's face it, the majority of the rain is falling near the equator because that's where our rainforests are, and that doesn't seem to be much different in the past. And when you have massive amounts of erosion on mountains, you take a lot of carbon out of the air. And when you take carbon out of the air, it reduces the greenhouse effect, and in effect, you actually cool the climate. And that is what occurs in the Carboniferous. The Carboniferous climate begins to cool, and we actually get glaciation on the southern continents. All right. Anyway, Mississippian period landscape, reptile here. You're starting to get. I don't know if that's exactly it. I wouldn't call that an archaeosaur, but it's something that is essentially beginning to look like what will be a dinosaur, and that is true. These are some of the earliest relatives of them. These right here, I believe this is probably one of the most ferocious amphibians to ever walk. It's like an amphibian alligator. I think it stood something like, I don't know, something like 6 feet long, 8 feet long, and definitely the apex predator of the time. And I'm gonna have to go back. I'll end up recording these again, and I'll get the names of all of these. But yeah, this is the time of like pretty much the gnarliest amphibian, and then of course reptiles are going to start to evolve further. They're going to start branching out, of course, because this is a reptile right here. They are starting to branch. So these types of things become as they evolve, they start to form. This will evolve into a reptile, and once you have the reptiles that can get out of the water more, their physiology begins to change. This is still obviously made this creature to be in swamps. It doesn't have scales. It still has a skin that most likely needs to stay wet for the majority of the time. You're in a warm climate, so cold isn't really a factor yet. But you're developing the eyes, basically, that are moving forward, so you get that straight forward, which most predators have, although you can still see off. But look at the mouth and the head. This is designed to kill. It's not a friendly animal. This guy's probably eating insects, probably very quick, trying to stay away from that for sure. And this is probably a result of these creatures. If you're going to survive in this time, these guys can move fast, I guarantee, on short spurts, but they aren't going to chase you for very long. So being young, if you're not an apex predator, this is the shape that's going to get you far and out of the clutches of these things. Carboniferous period global view. We have Africa. We have Laurentia right here. We have the Penthalastic Ocean. That's like the worldwide ocean before the Pacific. This is the Indian Ocean before the Indian, called the Tethys, and that is going to disappear in the next 100 million years, 200 million years rather. This is Pangaea pretty much coming together. As I said, you have glaciation down here on the southern continents. You have a huge mountain range going right through here as the Gondwana area and the Laurasia area even have combined and collided, building a gigantic mountain range. And again, you have water coming in, warm, super warm water, probably gnarly monsoon, and just tons of tropical activity because the heat is good, and you're eroding this mountain range as fast as it builds. And as it does, it's taking CO2 out of the air, and it is causing the climate to cool. And this is the Pennsylvanian period, 315 million years ago. This is it. This is Africa coming in. This is what's left of the Iapetus is now closing. Massive mountain range of the Appalachians. This is it. You couldn't find a better mountain range. This is the world's largest mountain range at the time for sure, getting upwards of 24,000 feet maybe. It was huge, and I believe it gets a little bit bigger. Here we are tucked away in the middle of a continent, probably getting blasted by rain. Actually, we're probably somewhere above the tree line, maybe even in the snow somewhere, because these mountains were like 20,000 feet, and Ogunquit was probably buried underneath all of that. 300 million years ago, this again, just huge mountain range right here, blocked away. The zipper is closing, so this is Laurentia, North America, Africa right here. You still have some interior seaways. Sea level is a little higher at this point. You have trenching over here, or subduction occurring, creating an island arc that is going to be crashing into the. Up until this time, for the most part, the the West Coast has been fairly quiet, and now it's starting to become active. This is sort of this is a shallow interior seaway, another one right here, and again, here we are located right in the smack of a gigantic mountain range the size of the Himalayas. So Pennsylvanian period, if I didn't say so already, the Carboniferous is divided up into two periods, at least by American institutes. And Carboniferous, it goes from hold on, 291 is the end of it, and I believe that 345 sounds right to be the beginning of it. I have to check but anyways, the earlier part of the Carboniferous is called the Mississippian time, and then the later part of it's called the Pennsylvanian time. So the way I remember it is M comes before P, if you're looking at time from distance. Anyway, or at least time from going from oldest to youngest. So our depositional environment, you've got Africa right here, you've got lowlands here, you got the shield, you got island arcs out here to the west. You're building sedimentary highlands right here from the erosion of these gigantic mountain ranges right here. On the little chart right here, we are smack dab right here. This is it. This is as big as we get. This is the peak of the orogeny. Africa has now collided. Continental crust has thickened. Everything is going up and down and getting crunched or shortened, as we call it. So equator right here, lots of erosion going on, and lots of carbon coming out of the air. And on the timeline chart, we are in the Alleghenian orogeny. Rheic Ocean is now closed, and here we are. Boom! This is a long-lived mountain building episode. Goes from about 300 and about 340 to about 260. So that's like 80 million years, and in a continent collision, that takes a very long time. What did we say the difference? So it's 359 to 299. All right, so that was so pretty much approximately half of that's the Mississippian, and then the Pennsylvania is the latter half of it. And yeah, there we are. Now, what kind of mountains are we looking at here? We are looking at Himalayan style mountains, 24 to 29,000 feet. That's as high as we have right now. Could be higher, could not be as high, but definitely in the 25,000 is a fair and easy. I have confidence saying that 25,000 feet is probably pretty accurate, at least some places in this mountain range. And this is what they look like. So, this is the cove. That's downtown. The beaches, I'm just kidding. They're actually like 6 to 8 miles underneath this. And they will not be seen for a very long time. Probably a good 250 million years before anything even begins to get close to the surface of where we are now. But so all of this material has been removed. Considering these are probably, let's see, 4 or 5 miles high. We're going to take all of this off. And then we go down another mile into the roots of these mountains, and that's where Maine is right now. Maine is buried. If we just assume that this is Maine right now, we would need to go down 6 miles, and that's the surface of where we are now. So when you walk out your front yard, it's 6 miles underneath this. Pennsylvanian period, you got a lot of insects, this is a time when the earth was very wet in a lot of areas because we were on the equator, a large chunk of the landmass. And because of that, we generated massive amounts of plant material and biomaterial, and that's why we have our oil reserves. And the Carboniferous is considered one of the largest petroleum producing areas on the planet. And it's from all these, like the world around the mountains and everything like that, on Laurentia and Europe, it looked like a giant Everglade. It was just one big giant Everglade with just tons and tons of just organic material rotting and being put into a swampy-like environment and had very little oxygen and anoxic. So what happens is stuff gets buried, then it starts to compress, and then it starts to heat up, and then it starts to convert that carbon into a petroleum material or bioluminescent material rather, and eventually you produce coal, natural gas, and oil, and that's the reserves came from basically a lot of the world looking like this at the time. And Permian. All right, now we go up to the Permian period. And the Permian period, this is when stuff starts to get crazy. We have Pangaea in its full glory. We have the Tethys Ocean blasting us with all sorts of moisture, creating swamps and stuff here, and swamps here, and swamps here, and swamps down here, producing tons of coal and tons of oil and all of that. We have a gigantic trench system off to the west, closing the Pangaea Ocean. We have subduction zone here off of China, subduction zone here. So now in subduction zone here in South China, closing the Tethys Ocean, and it's going to start pulling this crust this way, and it's actually going to start pulling this entire continent as well as India and Australia all going this way. And this trench right here is going to start pulling South America this way, and it's going to start pulling North America this way. And this is the Permian period. We have the mountains have now begun to start to erode a little bit. Our sediments are all spread out over here, down over here. Sea level is still, it's starting to drop, and the inland seaways are starting to go away. And so far, nothing's really started to rift yet. But the mountain ranges, we know that compression is starting to halt because the mountains are beginning to lose elevation. All right, so 275 years ago, million years ago, we have almost the mountains eroding into a very high, a highland. You're not seeing the mountain range itself. You're more or less just seeing the residuals of a sediment-laid highland as well as the ridges of the original mountain range. But they're eroded down to probably 10,000 feet, maybe less. Now, I'm not sure, but this is beginning to start to look like water starting to creep in. And this may be, this seems a little early for rifting to start to begin. So I'm not going to say it's starting, but it's possible. You can start to see some stuff. But I just think that this is seaways that are still intruding into the continent. And then we come to 260 million years ago, and we are starting to actually see some rifting here. This looks like it's starting to go into here. This is starting to make its way into here, and this may be beginning to start to unzip. And there may even be extension starting right here. So we'll go back one more. Yeah. I would say that this is starting to thin, and by thin I mean North America is going this way, Africa is going this way, South America is going this way. And what's happening here is as the mountains have begun to erode and the sediments have gone here and here, what's happening is there's less weight holding because the material's gone. And when you take weight off of the center, or say a mountain range that was holding down or depressing the crust, you have less pressure at the base of the crust, and all that molten material down there begins to, it's almost like unscrewing the cap of a soda can, a soda bottle, and it starts to fizz because that pressure begins to start the soda begins to expand, and it begins to push on the top, and it begins to start to want to release. And that's what's happening right here. The mountains are now gone, the weight is lessened, and all that root, that crustal root that had been pushed deep into the mantle, or the asthenosphere rather, has begun to start to migrate up and take pressure off of the material. What was once a very packed molten material is now beginning to expand. It's beginning to heat up. It's beginning to release. It's beginning to liquefy, and it's beginning to melt the base of this crust. And things are starting to get forced this way and this way, and basically what's going to happen is a very large area of magma is going to start generating underneath this mountain range, and it's going to try to find its way up. And now we are starting to see extension here and extension here, and these they look like mountains, but what they really are is they are grabens or troughs. So you're getting basically normal faulting right in here. As this goes this way, this goes this way, you essentially have the crust thin, and in between there's essentially areas where the centerpiece will drop, and it drops because there's really nothing underneath it to hold it up. So you'll have a center block that will be down dropped, and then on each side you'll have higher hanging walls. And as this goes further this way and this way, we will start to see more of these start to develop, and eventually this crust will thin, and the ocean is starting to come in. And that is represented by this stage right here, Mesozoic rifting. The continent has begun to split. It came together, it pushed everything up, it is now beginning to split. This area here is basically thinning. You're starting to see this right here. We're not quite to this point down here yet. We're just at the initial stages of it. So I kind of put it right here. And this is sort of the marine environment. You have the Appalachian Mountains, and they're now they're definitely eroding. You've got all sorts of sediments out here, and these red beds are made from the materials that the mountains were built off. And of course, you have island arc volcanism going on out here on the west coast now, because we had an island arc start to approach. We have reefs down here, evaporites, and we also have basins from all this material from this giant mountain range. So, mountain ranges don't disappear, they just get moved. And so all the weight that was here is now pushed out here. And so this area in here has gotten a lot lighter. And because of that, as represented here, things start to separate. And that's what I'm saying. You're going to start seeing this area right here. As I said, a centerpiece drops. You have two hanging walls on each side. And as it goes on, this will just keep fracturing, and or pieces here will just keep following suit. So this in here is represented by this right here. Again, right here is this right here, or up here, either way you want to look at it. So now we've come to Pangaea. Pangaea has the supercontinent Pangaea is formed, and now it's beginning to rift a little bit, and now we're going to start to create the Atlantic Ocean. And if you were going to look at New England about 250 million years ago, this is kind of what you'd see. You'd have what were once gigantic mountain ranges being eroded, and we're starting to see lower mountain ranges. You've got valleys filled with rivers, and they're kind of lush, and you have the remnant peaks of what was once just gigantic. These are probably, I don't know, 8,000-10,000 feet maybe. Most of these are probably in the 6,000 to 8,000 range now, foot range. Pangaea. This is what it looked like in all its glory. You had your mountain ranges here. You had mountain ranges here. This is the Tethys Sea, the Panthalastic Ocean, which is a kind of proto-Pacific. This is just a simplified map showing you the mountain ranges that were built, and obviously ours is one of the biggest right here. And about 275 million years ago, or this is arbitrary. It's just somewhere around in between 275 million to 220 million. You're going to come into an area that eventually is going to look like this. Over time, as the mountains rose and fell, the climate began to change, and as it began to change, it began to dry out, and over time we began to form a drier area, because we began to be located in the center of the continent, and this is representing New England. We began to dry, and we started getting away from the actual mud. Also, the mountains did not, because they began to level, they were not attracting the amount of moisture that they once were. So the area of New England begins to dry out, and it starts to look something like this. And these are all the marine sediments back when, erosion was high and everything, like just dumping out tons of silts and clays and sands and stuff like that. But over time, it begins to move its way in to savanna, and even more so desert environments. So probably something like Iraq might be what we would have looked like about 270, 250 million years ago. Mountains have eroded and worn down to rolling highlands and cut into their own sediments. New England is located far from the ocean and near the interior of Pangaea supercontinent, and has become very arid. And it's this part of the climate, when Pangaea begins to start drying out, this is one of the things that really helps reptilian evolution get going, because the amphibians were killing it with all the warm and moist and swampy areas of the Carboniferous. But once things start drying out, you need to figure out a way to survive without being wet all the time. And it is those animals that begin to really start to evolve, i.e. the reptile. One of my favorite animals of the time, the Dimetrodon. The Dimetrodon was cruising around between 290 and I think 275 million. I don't know, 280. They had a good life, span. They were very abundant. They are without a doubt one of the most abundant fossils of their time. So this is a extremely successful design. And if you think about it, I always think about, when I look at something like this, why this developed the way it did. And to me, it seems pretty obvious. You went from a very swampy, warm climate, and then everything began to air out and dry, and the glaciation of Gondwana lowered the temperature, and over time the land as a whole began to dry out and cool off. Well, those amphibians, they had to evolve and develop something to keep their skin dry, and that more or less came in the form of I guess you would say, scales. But in any case, the amphibian developed and evolved into something that it kept the initial shape, because this is a fairly good mode of transportation and locomotion. Plus, we hadn't developed anything else yet, so this is pretty much the design we were working with. You got sprawling legs, kind of like the amphibian. But what we have here is a sail, and when you have, this has been under a lot of scrutiny about what it really was for, and I'm going to make a shot at it myself now. And if the climate cooled and it didn't have that consistent warm 24/7 tropical feel, and it was wet, and then it started to change. Once you get to temperate climates, the nighttime and daytime temperatures vary wildly. One of two things needs to happen. You need to either figure out a way to keep yourself warm at night or die. And I'm a firm believer that these sails probably started to develop to give the animal more surface area, so that it could heat itself up quickly when morning came. It could also cool itself off, just depending on where it really wanted. Because think about it, at noontime, the sail's getting hit head on, so it's not really getting much of anything unless it decides it wants to lie on its side. But in the morning, in the evening, it's soaking up. It's making optimal use of its sail by absorbing heat and energy. And that's kind of when you're going to need it. You're going to want it in the morning. You're going to want it in the evening to keep yourself warm overnight. And I think that's a good call on maybe a purpose of this, because this species, all of them have it, and it worked for at least 10 million years. And these fossils of these creatures are found everywhere, all continents. Obviously not Antarctica, because we just can't get to the rocks, but I'm sure they're there. And then look at the skull. It kind of kept that thick armor skull of that one apex predator amphibian, but now it's added something. You really can't see it here, but I know this because I've been studying this creature. It has different sets of teeth, and it is this particular fact that this is one of the first animals to actually have that. In other words, you have sharp teeth here, maybe even molar type teeth, but then you have some four sharp teeth in the front. And you look at a cat, you look at a dog, you look at a bear, all of the mammals have this particular trait. And this particular species, I believe, has 3 different types of teeth. That is one of the most defining characteristics of a mammal. And mammals have different types of teeth. And not to mention the fact that it also, you can't see it, but reptiles, I believe, have 2 holes in the skull. Mammals have 3. And synapsids have 3. I forget how that exactly works. But the point being is that this is really truly a part of our evolution. It's also part of a reptile evolution. But in the grand scheme of things, this is considered a mammalian-like reptile because it possesses some traits that we follow through. And I know that the 3 holes in the head are one of them. So it has basically a skull that has pretty much the exact same design, not so much the design, but the amount of parts in its skull that we have. It's just it's arranged slightly differently, and over time they sort of rearrange themselves slightly to make the skull that we have, and then every other mammal. But this is in the direct lineage of mammals. At some point, there's a split where you get sauropsids and I believe diopsids. We are believe diopsids. I may have to edit this, but the sauropsids end up going to the reptile, which goes to dinosaur, and then the diopsids end up going to, or is it synopsids? I forget. I'm going to have to edit that. Yeah, the sauropsids and synopsids. It's synopsids. Synapsids are the ones that go to us. So sauropsids, synapsids goes to mammals. Sauropsids go up to reptile, and then crocs and everything like that, dinosaurs. All right, so that's the Dimetrodon, a very key creature in our evolution. It loaded the Permian period for about 10, 12, I don't know, I have to look it up, but maybe more. Very successful species. And it's interesting is that this species both had carnivore and herbivore varieties, so you don't really see that often. This definitely was a carnivore, though. And when it was a carnivore, it was the apex predator in the area, wherever it was. Here is another Dimetrodon, it's sort of hanging out. Got the sail, teeth. Again, you're noticing it's the different types of teeth. This is interesting. I never saw that. These must be little Dimetrodon right here. I don't know. I wonder if they look the same. Probably not. Maybe because these are actually extensions of their spine. But cool picture. And so in the late Permian, this was really earlier Permian, this guy evolves into these. And what we have here is, this is just an incredible picture of the late Permian ecosystem. So you have these here are basically crocodilian-like reptiles, and this is when the split happens. So at some point in the Permian, the Dimetrodon lineage, more or less, we said one way went sauropsids, the other one went for synapsids. We are synapsids, the mammals, and so the sauropsids basically went into crocodilian-like animals like this. Now remember, these 2 lineages came from the same thing, but they diversified. And then you have the gorgonopsids. And so these right here were without a doubt the bear, or we'll just say the tiger or the lion of the Permian. They are the gnarliest, meanest. These are the apex predator. And if you look at them, it doesn't take too much imagination to realize that we are very related to these. Look, you got the 2 canines right here. You got the 2 down here. It almost has a lion design to it, or that quadrupedal, just robust design. But my God, look at the size of the mouth on this thing. These things were killers, and they hunted, and they were in charge of everything. But again, the dinosaurs more or less came out of this design right here. We came out of this design here, as well as obviously cats, bears. This is the mammal lineage right here. This is the reptilian lineage. We have now diversified. These are over here, sort of the herbivore reptiles. Over here, right here, these are sort of, these are going to go into, actually, I'm not really, I mean, I would make a guess and say that would go to the ankylosaurids, but anyways, these are all reptiles, more or less, with the exception, these are not reptiles. These are synapsids, and I do not believe we classify them as, these are basically, they're not mammals, but they are going to become mammals. All right, Pangaea around 260. I think we already looked at that. All right, so the Permian period. The Pangaea supercontinent comes together, affecting the Earth's climate. Pangaea separates the Earth's oceans, thus changing oceanic circulation. The central Pangaean mountains, which is the Appalachian, reached their zenith in height, approaching and possibly exceeding the Himalayas. These massive mountains begin to erode extremely quickly due to the location near the equator. The climate becomes increasingly warmer and dry, with large desert areas and massive seasonal fluctuations. And then global temperatures spike rapidly near the end of the Permian. Life is flourishing and has evolved to enough to occupy all of life's niches. Although apex predators were not mammals as they were, although apex species were not mammals as they were reptiles, they were mammal-like. And now we are going to discuss extinction events. And I'm going to hold off here because this is going to be a discussion in itself.